All right, welcome to day 2. If you haven't yet, start thinking about how we ended on Tuesday, talking about O2 and H2O and why they are so different at room temperature and pressure. So contemplate this, chat with the person next to you, write out what those intermolecular forces are, because that's integral to understanding why O2 is a gas at room temperature and pressure and why water, though a smaller molecule, a lighter molecule, why that is a liquid. Okay, so just chat with the person next to you, make sure you guys are on the same page about why this is true. All right. So what are the intermolecular forces between O2 molecules? I'm hearing it whispered, but I should be hearing dispersion. Okay, so if I were to draw an O2 molecule, right, it would look like this. It's my lone pairs. And yeah, oxygen is an electronegative element, but it's paired with itself. And so the 4 shared electrons between those 2 atoms are equally shared. So there's no area of partial positive or partial negative on that molecule. So when these things come together, like imagine I had cooled this down, we were sitting at like 0 Kelvin and we'd all frozen to death long ago. These guys would be sitting next to each other. And the only thing holding them together is dispersion forces. All right, we know from 1210 or whatever you had before this and from Tuesday that dispersion forces are very weak. So as I turn up the temperature on my block of O2, I don't need to add very much energy to pull those O2 molecules out of the group because they're just not holding on to each other very strongly, right? Those dispersion forces are weak. In really significant contrast, H2O molecules love to interact with each other, right? And they interact very strongly. So each water molecule can hydrogen bond with 4 other water molecules. Okay, so it's not just that it can hydrogen bond, there's 4 places. It essentially has like 4 hands to hold with other water molecules. I'm still thinking about ants. Right? So each place here is an opportunity for that water molecule to hold on to another water molecule. All right, so again, I can make this cold and have a brick of ice sitting here, and as I turn the temperature up on it, compared to O2, I'm going to need to add a lot more energy because those molecules are holding on to each other so tightly that I need to put in a lot of energy to yank them out. So it turns out at this pressure, 1 atmosphere, and whatever we're at, I don't know if I have a thermostat in this room, but like 70 degrees Fahrenheit, oxygen is a gas. We've already gotten to that place, and water is still a liquid. Okay? So this is many, many hydrogen bonds. And that dictates, again, these are small, but they dictate the physical properties. Okay, so that's what I wanted us to get that out from Tuesday. I have a couple, you guys don't have this next slide, but I want to make a couple like administrative announcements before I do any questions on this. Give me like a thumb meter on like thumbs up, you're feeling good with how much you remember of intermolecular forces. Thumbs down, you're like, I don't remember ever hearing that term. Somewhere in the middle. Okay. Thank you. That helps me get my head wrapped around where we are. Okay, so a couple announcements. So 1, I heard from enough of you that I needed to make this announcement. If you love chemistry and on Tuesday you were like, wait, I like chemistry. Am I in the wrong class? I didn't pitch that correctly. I am just usually concerned about bringing in my students that like come in and hate chemistry, and I want you to feel welcome. But then by doing that, I didn't also extend a warm hug to all of you that do love chemistry, and of course you were in the right spot. But I just like heard enough like slight anxiety that I had to say something. So sorry I screwed that welcome slide up, but you are all in the right spot, and I'm excited to have you here. I've heard a couple requests to change sections, whether that's this lecture, the lab, or your recitation. I don't do that. That's a Holly Wheaton question. That deadline, I think, is the 5th of September. So after that, you cannot change sections. If you're like, I gotta change sections, that's gonna depend on if they're full or not. But if you need to do that or really want to, go to Celeste 110, talk to Holly Wheaton, okay? I posted the Exam 1 supplemental info on Carmen, and I'll point out that to you where I put it. This is what you will have for the first exam, okay? So the equations that you will have in front of you, the constants that you will have in front of you. I recommend having that available while you do the Pearson homework, because Pearson usually doesn't embed that information. So you might get to a question on Pearson and be like, I don't know how to answer this. That's because Pearson is stingy with the content that they put into the questions. So be aware that you will have a set of equations, and you already have that sheet, so you can do your homework while you have that next to you so that you know what you will have. All right, and I'll point that out in a second. All right, so if you were doing the graded Chapter 11 review and you were like, oh my God, I don't remember any of this, I just want to remind you that the LRC is open and you should go stop by if you need help reviewing. I went to the schedule, and I posted this on Carmen as well, but the TAs that are highlighted in yellow here are either TAs for this semester or have been a TA for my class in the past. And so they are familiar with the way that I teach. They're familiar with my recitations. So they are all great resources for you. All right? Questions? Okay, I'm just gonna I wanna point out to you on Carmen where, so here at the top of that lecture, exam 1, that's where that helpful info, that's what you have on the exam. All right? And then if you go to home, just so that we all know where this resource is, and you scroll down, I forget that this is down here. Let's see, you need academic help. All right, I just put this in there. So if you're like, I wanna like go see my TA, now you can find them on this. And if you're like, well, I can't go see my TA, at least you could go see another TA that has had me before. In theory, any of these hours should work for you, okay? All of our TAs are exceptionally talented and smart and can help you, but if you want someone that like knows my style, those are the people, all right? Questions on logistics? We're all happy-ish? Okay. All right, then, if no one's gonna stop me, let's start in on the new content of 1220. All right, so we are getting into chapter 13, the properties of solutions. My goal is to get through sections 1 through 3 today. I'll do my best to keep us on task. All right, so to start with, I have to just make sure we are all on the same page with some basic definitions, all right? So a solution, by our definition in this class, is a homogeneous mixture of 2 or more substances. Your default image, at least mine is of a liquid and mixing with something else, but we can have solutions in the gas phase or solutions in the solid phase. But in this class, we will actually be focusing on those liquid solutions. I want to highlight the word homogeneous and remind ourselves what that means, that it's the same throughout. Our solution is the same concentration throughout. All right, so for example, when you take a sip of Coke, you expect that Coke to taste the same as the last sip of your Coke, because that's homogeneous. All of the, super healthy stuff that's mixed up in there is staying in solution and is equally distributed throughout, right? So your last sip is not different than your first sip. Whereas if you were eating cereal, for example, and you had like Cheerios and milk, each bite is a little bit different. It's not homogeneously mixed. That's a heterogeneous solution, and every scoop is going to be a little bit different. All right? So our two substances, we have to have two of them, and the first one is the solvent. And usually we talk about the solvent as the substance that we just have more of. For us in this class, our solvent is usually going to be water, but there's no reason why we can't have another solvent. And then our solute is the thing that we have less of. Okay, so we usually think about taking our solute and dissolving it into the solvent. All right, so this is the boring part. I need you to know these definitions. All right. So let's take a look at some of these and what images might pop up into your head. Right, so again, we can have a solid solution, all right? So we've got gold here mixed with something else. And if you might argue with me and say, well, that's not homogeneous. I could like shrink down to a place where like I only grab the gold versus the copper, right? But like at the level that we can actually deal with, any piece of that gold is going to be about the same, right? A heterogeneous solid solution would be where there's clearly differentiation between one layer and the other. All right? We won't talk any more about solid solutions after that. We can have gaseous solutions. For example, what's around us right now is a mixture, a homogeneous mixture of mostly nitrogen, oxygen, carbon dioxide, and argon, right? Those are all equally distributed around us. And what we'll focus mostly on, liquid solutions. And so we can take solid. What I want to point out, though, is it's not just a liquid with a liquid. We might take a gas solute and put it into a liquid. We could take a liquid solute and mix it, or a solid solute. All right, so we'll change the phase of that solute as we put it into the liquid. All right, so this is where we're going to spend our time. Okay. We are going to get into the why. Why do things mix? And I want to lean, I'm going to lean on your intuition first, okay? So I've set this system up where on one side I have oxygen, and on the other side I have argon. There's a partition between them, okay? And I pull the partition out. Will those two gases mix? Thumbs up if they do, thumbs down if they don't. Good. I pull the partition out, and they mix. In other words, what I get out of this thought is that, yes, there is a natural tendency towards mixing. Okay, I pull that partition out, and I do nothing. I don't have to do anything. Those oxygen and argon particles are going to mix, and then I will have a homogeneous mixture of them not too long away. Okay, so this is the natural tendency towards mixing. And what drives it is a thermodynamic quantity called entropy. Okay, so we're going to talk about two thermodynamic quantities. One is entropy. And entropy almost always, we will see a caveat to that today, but entropy almost always drives or encourages the mixing process. All right? So for those of you that are sitting there right now and like, wait, hold on, remind me what entropy is. Let's define it. Okay, so entropy, which is usually denoted with capital S, all right, it's a state function. Entropy, I will say, is the tendency for energy to disperse. Okay? We will, in chapter 19, really delve into entropy with more rigor than me just telling you that simple definition. What you might be more familiar with than that is that the second law of thermodynamics is also often sort of in pop culture referenced as the universe tends towards disorder, right? And so when I move that partition, those two sets of molecules are not going to stay, well, one is a molecule, one is an atom, but they're not going to stay separated. They are going to take up all the space, and they're going to become more disordered, all right? For now, before we get into chapter 19, all I need you to know is that entropy almost always encourages mixing. Okay? So that's your take home. That's all. That's primarily what I need you to know about entropy right now. Okay. So how do we decide? We know that we've got this entropy thing that's going to encourage mixing, but not everything mixes. So there's got to be something else that's going to help us decide if that process happens. Okay? So the ability of substances to form solutions or a mixture depends on, one, we just talked about it, our entropy, and then two, the enthalpy. Okay, so our other really big hitter in thermodynamic quantity is the enthalpy change as we mix two things. All right? So this is why we talked about intermolecular forces on Tuesday, because the enthalpy of mixing of the solution process is going to depend on the intermolecular forces between our solute and solvent molecules. That's what we're going to have to make a judgment on. Are these new interactions that we're making, are they strong or are they weak? Because that is going to dictate the enthalpy of this mixing process, and that's what we need to know about. All right, so entropy, remember, generally encourages. And then enthalpy, I'm going to say here, this is, I'll say it depends on the IMFs between our solute and solvent molecules. And we're going to make some judgments. If they're strong, okay, so strong IMFs encourage mixing. And then we'll find the opposite is true as well, that if our solvent and solute molecules have weak intermolecular forces, that is going to discourage the mixing process. Okay? Okay, so given those two things, all right, I'm going to ask you to delve deeper into your 1210 knowledge. Okay. Knowing that, I want you to stop and think, will two gases that we can treat as ideal always form a solution, or will some not mix? Okay, so take a minute to chat with the people around you, and don't just come up with yes or no, justify your answer. Why will gases always mix if we can treat them as ideal, or why might they not mix if we can treat them as ideal? All right, what do we remember about ideal gases? What assumptions were we making about our gases? Does anyone want to volunteer something? Okay, I won't make you say it out loud. We made two assumptions. If we could treat a gas as ideal, right, this ideal gas is a hypothetical, it doesn't really exist. One, because ideal gases take up no volume, okay? What's more important to us is that we also said ideal gases exert no forces on each other. So we totally ignored all of their IMFs. All right, so that means that when I put two gases together, if I can treat them as ideal, they should always mix because entropy will encourage them to mix because they're increasing the disorder, and there is no enthalpy consideration, right? So we don't have to think about how they interact because we treat them as ideal, and within that is an assumption that they don't interact. So we should always, entropy encourages this, pushes this forward, and there's no enthalpy consideration. Because we're thinking about ideal gases or real gases that are considered ideal. Okay, but that obviously will break apart once we go into the condensed phase, which I've already told you we are going to do, because now in the condensed phase, our molecules certainly interact with each other, and they're really important interactions. All right, so we are going to break down the solution process, all right? I'm going to take cup A, which is a liquid, and cup B, and I am going to mix them together, and I'm going to break down how I think about the enthalpy in that situation. All right, so I've got my cup of A. All right, and I've got my cup of B. And I'm wondering, can I make a cup of A and B that are mixed, like a homogeneous solution? All right, so what does that mean? What do I have to do to make that happen? All right, so on the left side here with our pure A and pure B, if I were to zoom in, I'm thinking about this network of A's, and they're all connected and held together in the condensed phase by their intermolecular forces, right? And then I look in B and I say, oh, well, hi, B's. You're also held together by intermolecular forces, right? All right, well, what do I have to do if I'm going to make a homogeneous solution? What does that look like, right? So a homogeneous solution of A and B might look like A's always interacting with B's, and B's always interacting with A's, right? So if I'm going to break this process down and say in my final solution, I'm only going to have A-B interactions, okay? To get to only having A-B interactions, my first step is that I have to split apart all of the A's. I need to break all of my A interactions. All right, so I need to think about in this process, of course that's not what happens. When I mix water and ethanol, I don't actually take all of them into the gas phase, but this is like the theoretical approach to it. I am pulling all of them out, so I am breaking all AA and BB IMFs. All right, so when I break an interaction, when I break these like very weak bonds, that costs energy. I have to put energy into the system to make that happen. Hopefully this is sort of ringing a bell from 1210. Okay, this costs energy, which means that delta H is positive, it's greater than 0, and this is always an endothermic process. This side of the equation where I'm breaking these interactions. They came together because it lowered their potential energy. So if I'm going to pull them apart, I have to put energy in to make that happen. Okay, that's endothermic. That will discourage the process. That costs me something. That doesn't encourage mixing. What does encourage mixing is that on the other hand, yes, I have to break these interactions, but I get to make a bunch of AB interactions, right? So this releases energy. Over here, delta H is always less than 0. It's always negative. This is always exothermic. I am taking two things in theory that are infinitely separated, and I bring them together, and maybe they form like a dipole-dipole interaction. That lowers their potential energy. That energy has to go somewhere. It gets released, usually as heat, and it's exothermic. Okay? So in our battle of whether or not this process happens, we are going to compare the size, the cost of breaking up A and A's and B and B's, and then sort of like the benefit. How much energy do we release when we bring them together? Okay? So your book, we can take this and make it very simple equation, all right? So we are interested in the overall process, okay, delta H solution. So overall process, okay? We just looked at delta H of the solvent, that was my AA. Delta H of the solute, that was my BB. Both of these are positive. These are always going to be endothermic, okay? And then we have delta H mix. The benefit, the new IMF that I get to form, that's always negative. That's always exothermic. If the overall process is exothermic, that must mean that delta H of solution, all right, so now this is specific to the exothermic process, this is going to be negative. That means that delta H mix, which is a negative number, so I'm going to put a negative in front of it. Now that's a positive number. That means that this is bigger than delta H solvent plus delta H solute. All right, and your book, I like this image, your book puts this into a picture. All right, so we've got our positive contributions, the endothermic costs. Here's delta H of the solvent. Here's me taking my condensed phase and pulling them all apart, okay, breaking them up. Same with my delta H of the solute. In this case, it cost me a little more to do that, right? So that's my overall, here's my cost. There's the endothermic cost of doing it, but I get to bring them together. So my delta H mix in this case is a bigger arrow, a bigger negative arrow, which means that this overall process, there's delta H of the solution, is negative. I wound up lower than when I started because these two things like to mix with each other, okay? This encourages mixing, okay? Remember that things tend to like to minimize their potential energy, and in this case, mixing minimizes their potential energy because we must be making some really strong intermolecular forces between our A and B's, okay? Because it's exothermic, right, we have a release of energy, and again, that, well, it's probably going to be in the form of heat. So if I took A and B and it was an exothermic mixing process, that flask in my hand would feel warm. Okay? Remember, I can't destroy energy. It's got to go somewhere, and it's going to increase the temperature of my flask, of those molecules, all right? So this will feel warm. And that is characteristic of an exothermic process. All right, so if it's exothermic, entropy is still pushing this forward, and now I have enthalpy pushing this forward as well. So that would certainly happen. I would expect something with a negative delta H solution. I think those two things are going to mix for sure. All right, and now we have to contend with what if it's not exothermic? What if it were an endothermic interaction? All right, so now again, the same equation. We are considering the same variables, but now when we look at the cost, all right, so there's a really big cost to splitting up our solvent. Okay, still a decent cost for splitting up our solute. All right, so here's our overall cost, the addition of those two positive things, right? And now when I mix these two together, yeah, it's still negative. That's always going to be negative, but it is not a very big negative number. Not enough to be worth the cost of splitting them apart. So I am not optimizing intermolecular forces by doing this mixing process, which means that this delta H solution is positive, which means this is an endothermic process and may not happen. Okay? It is not going to encourage it. It will discourage it. However, some endothermic mixing processes happen because if it is only slightly endothermic, entropy will give it that extra push to happen. Okay? Remember, entropy is usually pushing us along to say, yeah, no, you should mix, definitely do that. So we do have some endothermic processes. So like I might mix two solutions together and I see them mix, but I feel the flask getting colder. That means that that process requires extra energy. It requires this extra energy right here to happen. And it's pulling that from the thermal energy. So it's cooling it down because it's taking some of that thermal energy and using it to make these less than optimal new intermolecular forces between our A and B. All right? So we'll say it can still happen, right, like an adult, can still happen because entropy is also encouraging it. Okay, so we are going to take, this is an important equation here, and being able to work with that is going to come up on your exam. We will do a simple practice problem on the next one where you just work with numbers and get the definitions down. And then we will take that equation and we're going to plant it on a bunch of specific examples. All right? So take a second, work this problem. This is certainly something that could come up on an exam. So maybe look at it by yourself, make sure you know how to calculate it, and then answer the two other questions. Feel free to talk with the people next to you. All right, guys, so let's take a look at this. This is a plug and chug type question. You just got to make sure you're putting the right numbers into the right place. Be aware that we might give you this, but we could give you delta H of the solution instead and ask for you to tell us what delta H mixes, all right? Those are the kinds of ways that we tweak problems. But I'm going to say, all right, I'm going to be lazy and I don't want to write units. So this is, what did I say? This is 5. This is 9. This is -20. I add those three numbers together. I get -6. That tells me that this is an exothermic process, all right? 6 kilojoules per mole were released when I mix that together. So that energy has to go somewhere. It's going to go to heating up my flask. It should feel warm. I can make one more statement about this that I didn't ask you. I could have pushed you a little bit further and said, what can I say about my A-B interactions? my solute-solvent interactions. Would you guess that they are strong, or would you guess that they are weak? And hopefully you would say, I'm guessing that they are strong, right? Because we're bringing them together. They actually really like to be together, and energy is released. Okay, so I would guess my solute and solvent IMFs are strong. And I would guess that for any exothermic process. Okay? You know, let's hedge this sentence. We're going to say they're relatively. All right? So let's actually take this and put it onto a real life example, one that we are very familiar with. Okay? At some point, I imagine all of us have put salt, as in NaCl, into water. And again, something you are familiar with. It dissolves, right? And this is always kind of like, you're just like, yes, I take that for granted. Salt dissolves in water. But does anyone, like when you guys learned about bonding, are ionic bonds really strong or are they weak? They're strong. They're like a positive and a negative sitting right next to each other. And I say, well, actually, these really, really strong bonds, you put them in water, and guess what? They just fall apart, right? Like, that is kind of confusing. So let's break it down. Why does that happen? Spoiler, it's intermolecular forces. All right, so let's break it down, and we're going to keep this equation with us so that we can sort of like plant this there, right? We are taking salt, and we're putting it into water. So salt's going to be my solute. And maybe I looked this up earlier today. I can't remember. I think I might just use some fake numbers. So we are going to have a really big positive delta H solute. Okay, that's the lattice energy of our salt. Okay, that's me yanking. How much energy would it take for me to pull NAs out of that, Na pluses out of that lattice of Na plus and Cl minus? So that's really costly. All right. Then I've got delta H solvent. Well, for water, that might be something around 50 kilojoules per mole. Right? And that's, you know, for intermolecular forces, that's pretty strong. Those are hydrogen bonds. This is our salt here, NaCl. And then the key here is what is happening when I mix them together. Okay, so there's my chunk of crystal NaCl. That's not how it dissolves. When salt dissolves, it splits up into its ionic components. So I'm going to have an Na plus and a Cl minus. And every time those dissolve, I get hydrated ions. So this was the last thing we didn't quite get to on Tuesday, but so here's my, this is all very, what color will pop here? All right, here's my Cl minus, oh no, that's terrible. Maybe try purple. All right, Cl minus, right, a full charge, and look, I've got hydrogens all the way around it. Okay, so each time I dissolve a unit of NaCl, I'm going to have a Cl minus surrounded by a bunch of little positive charges, but a lot of them. All right, so those are my ion dipole interactions. So I get to make many ion dipole interactions, which is the last IMF that we didn't get to on Tuesday. Okay, but these wind up being, right? This happens for every single Cl minus, every single Na plus, and I've got a whole shell of waters surrounding them in 3D, and I'm crowding all of these positive H's and all of those negative O's around Na plus. Okay, and so we wind up finding that a solution does form, and you guys know that. We know that we can make a salt solution, and that's because delta H mix turns out to be an incredibly large number as well. It's an incredibly large negative number. All right, so this is my ion dipole. When I add these three together, and this is true, these aren't the exact numbers, but I do know that you're going to wind up getting a slight, what did I do, 4, 4, 5? Okay, so this is going to be plus 5 kilojoules per mole. All right, it is slightly endothermic. but it's not crazy endothermic, right? I am still, and so the thing that pushes this forward, it's a little bit endothermic, but not crazy. So there's not a huge barrier there. But I am definitely increasing my disorder because I used to have all of my NAs and CLs in a perfect lattice with only one real configuration for them. But now I dissolve them in water and they're going crazy all over the place. So there's a huge increase in entropy. All right, so this process happens, right? It happens because of these really strong ion dipole forces. All right, so we're going to add that ion dipole off to the end here on our spectrum of IMFs. All right, so there they are. I think there's maybe a figure. There we go. So you're like, why are those so strong? Well, remember that this is the electrostatic potential energy. Now, with an ion, one of those charges is a full charge. So let's say we're looking at the chloride. And this other one over here is a partial positive. But compared to, say, dipole-dipole, those were both less than 1 before. But now we're dealing with full charges. And so these are very strong electrostatic forces. And that's what drives salts to just fall apart in water, which, again, if you think about it, is kind of confusing. All right, so I want you to take that information and apply it now. Instead of trying to take a salt, now we're going to work with calcium chloride. Instead of putting it into water, we're going to put it into heptane. All right, and so let's think about, will this happen? Okay, so my quote-unquote IMF type and strength for calcium chloride, right? It's not really an IMF. This is these over here. This is a ionic bond. And it's incredibly strong. And the lattice energy, I think I did look this up right before class, is 2,258 kilojoules per mole. Okay? So strong, right? How about our heptane? What kind of IMF does heptane have between itself? Dispersion. Yeah, so those are weak. Okay? They're weak. I might give this like I called it a 30 kilojoules per mole. All right, now let's think about our heptane calcium chloride. If it's going to dissolve, ionic compounds have to break up into their ionic components. And so I'd be thinking about Ca2+ interacting with a heptane. So the question is that going to be very strong? And the answer is no, because that heptane is nonpolar, so there's no permanent dipole for it to interact with our ions. So we would wind up getting this is still a negative number, and it's probably a pretty big negative number. I had to guess this, okay? It's a big negative number. So those heptanes are still like, hey, I would love to sit next to you. That is a very strong interaction between heptane and Ca2+ in comparison to a heptane with a heptane. But from from the ionic compounds perspective, it's like, no way will I break up this lattice to interact with you. It's not favorable enough. Okay, so I would wind up adding these together and getting a wildly positive number. And so this is so endothermic, it doesn't happen. Okay? So, and again, to dissolve, it's got to split up Ca2+ and 2Cl-. We're not thinking about it as dissolving in little units. It's got to split up into the components. So in this case, I do not have a solvent that can support that. It is not offering strong enough interactions with those ions to get that ionic compound to just fall apart, right? So if I put calcium chloride into heptane, I'm expecting to see that salt just sink to the bottom and sit there, okay? It won't dissolve, right? And we can do that. We can do some quantitative analysis with an equation like that, all right? Questions on that? Yeah. Okay, so the question back here, like, how are these interactions stronger than within here? Well, they're not individually, but there's so many of them, right? It's not just one water that can sit around a Cl minus. I've got in this image 1, 2, 3, 4, 5, 6, right? So it's like this whole shell. And then even a shell around that is probably contributing. So it's like, it's an aggregate. It's not the individual one ion dipole interaction. It's that this happens many, many times. Okay, so think through, now we've done an example here. Think through what this, will pentane dissolve in heptane? All right, so think through that. What might those values be relative to each other? Are they very big? Are they very small? We're going to lead ourselves to a very common phrase about making solutions. So give me a thumbs up if off the bat you think it dissolves, or you think, or they're going to mix, or if they don't mix, thumbs down. Okay, all right. Let's look at this together. So pentane. What's the pentane-pentane interaction? Dispersion. All right. What's the heptane-heptane interaction? Dispersion. What's the pentane-heptane interaction? Dispersion. These are all probably about the same value. I would guess that when I do this, when I get a delta H of solution, it's probably near 0, because these are such similar molecules that their interactions are probably real similar in size when it comes to their delta H's. So I would guess that this is about 0. And they mix because of entropy. All right? And we are working our way towards the phrase that I think most people are familiar with. If we all heard like dissolves like, this is like the scientific underpinning of that, right? When we dissolve like things, our delta H mix is probably about the same size. So it's probably equal to the size of these two things. So there's nothing holding them back from mixing, right? Because the interactions are the same. All right? We could do a similar analysis where we look at water and heptane. All right? So now let's say, what's water's interaction? Well, those are H bonds, and they're strong. And they're strong. These are still dispersion. And I'm going to call them weak. And then I'm going to have dipole and what we call induced dipole, which this is getting into the weeds. It's like medium strength. But not strong enough. These two will not mix. So I guess, this is at like 50, this is at 30, and maybe this one's at like -40, right? And we're still going to wind up with a big positive number, so big, too big for mixing. And I know this to be true because when I put water and heptane together, they sit on top of each other. They're immiscible, and we'll talk about that definition, hopefully in a little bit. All right? So that's too big. Those water molecules to solvate heptane have to give up so many awesome hydrogen bonds for these really weak interactions, and that just doesn't happen. Okay? All right, so again, this is our like dissolves like. When we think about will this process happen, we're saying, what are we giving up? What are these AA and BB interactions? What are we making? These AB interactions. If we want the process to happen, we want to maximize the strength of our solute-solvent interactions. That tends to happen when our molecules are similar, okay? So when we maximize these interactions, that's greater solubility, and that usually happens when the molecules are similar. So that's where that phrase comes from, okay? That these two, right, we're doing this like battle, that these two, their absolute values are about the same, okay? Or we have an even stronger delta H mix. Okay. So let's take a look at, oh, I have some general rules of thumb for you on this. All right, so ionic compounds and polar molecules. So for us, polar molecules, a good thing to look out for are those electronegative elements in the top right corner. So F, N, O, Cl, S, P. Those are going to likely dissolve in polar solvents, okay? Because they are going to be able to hydrogen bond or have dipole-dipole interactions, and so they will dissolve in polar solvents like water because they can also have those interactions. All right? Ionic compounds have to go into polar solvents because they won't split up unless you can offer them strong and many ion-dipole interactions. Conversely, nonpolar solutes typically dissolve in nonpolar solvents. All right, so for that, I'm looking for CC or CH bonds, right? Those are all nonpolar. And I'm looking for, I'm going to say that's probably, those are not going to dissolve in polar solutes because they can't offer good IMFs. My slight nuance or caveat to remember is that when you see carbon tetrachloride, remember that that's a nonpolar molecule, even though the CCl bonds are polar. Remember, because it's a tetrahedral, all of those dipoles cancel out. Okay, this is my one nuance, okay, so that this is nonpolar. A nonpolar molecule. Okay, so I would expect that CCl4 to be more soluble in something like hexane than in water, right? Because it doesn't have a dipole to offer water. All right, I think I have a question for you guys. Good, this feels like a good time for you guys to take a break and think about something. Let's predict, okay? So now what you know about like dissolves like and the interactions that we're looking for. Here's acetaminophen on the left, and then ibuprofen on the right. Which will be more soluble in what? Can you make a guess at that? Okay, so point in the direction of the molecule that you think will be more soluble in water. All right, guys, so I'm looking at this, and hopefully you had this gut reaction. All right, I want to see who wants to spend time with, who can like offer some hand-holding to water. And I'm going to look for polar groups, especially ones that can hydrogen bond. So I look at acetaminophen, and I see that there's a group down here, and I see that there's groups up here too. And then I compare that to ibuprofen, and yes, ibuprofen has this group up here, but then it's got this big non-polar tail. And water will not want to interact with that at all. It'll be like, no, you're going to make me solvate that? I don't think so. I don't want to do that. Okay, so I'm going to guess, just based on looking at these structures and looking for those polar groups, that acetaminophen is more soluble than ibuprofen. And then you go to Wikipedia, as good scientists do, of course, and you say, all right, look, solubility in water. At 20 degrees Celsius, I'm comparing them. I can put 14 mgs of Tylenol into 1 ml of water, and that will dissolve. I can only put in 0.021 of ibuprofen. So just by looking at the structure and evaluating where there are polar and like hydrogen bonding opportunities, we can make a really good qualitative guess about solubility. All right, so I look at this, it's like 700 times different, right? And that's largely because that ibuprofen is going to have a much smaller negative delta H mix, because I'm not going to have good, strong IMFs with that nonpolar tail. All right? So this is actually going to help us segue, right? I just talked about the solubility in water. So this is a good time for us to define solubility. All right? So let's go back to salt and water. Again, it's something that we've done. If I have a cup of water and I put 1 gram of salt in and it dissolves, okay? I say I'm going to do another one. I'm going to put another gram of salt in and it also dissolves. My question to you, can I do this forever? Can I keep adding salt and expect for it always to dissolve? You are all shaking your heads no, because you already have this knowledge. At some point, the salt will stop dissolving. I will reach saturation and I can't dissolve anymore. All right? You guys already know this. No, something called the saturation point. All right? I'm reaching saturation. So we want to define these two terms, saturation and solubility. All right? So a saturated solution is the dynamic equilibrium, and we're going to talk so much about equilibrium, but we haven't quite gotten there, but I'll try and walk you through it, is a dynamic equilibrium between undissolved solute and dissolved solute. So it's at a point, what did I say about this? We can't dissolve any more solute, okay? Which means if I add more solute, the concentration in solution won't change. I'm just going to make a bigger pile of salt at the bottom, right? So we can think about it for salt as like, hey, I've got NaCl solid sitting at the bottom of my cup. Some of it is dissolving and making Na plus in the aqueous phase and Cl minus in the aqueous phase. But at the same time and at the same rate, I have Na plus and Cl minus going back and resolidifying. Okay? So that's the dynamic equilibrium part. It's not that like when I put salt into solution that like some atoms are destined to be in the solid phase and some are destined to be in the aqueous phase. They are constantly changing, but at this saturated point, my concentration has reached a max. I can't put any more in. All right, and so we usually talk about the solubility of a substance as the amount I can put in, the amount I can dissolve, right? The amount that can go in until I hit the saturation point. Okay, beyond that, I will just be dumping more solid into my cup. All right, and solubility, we'll note at this point, is usually in grams of solute. And it's going to be either in volume or mass of the solvent. We just saw it in volume of the solvent, but I'm going to put this in grams of the solvent because that's going to be consistent with the graph that we're going to look at in a bit. All right? So grams of solute per a set amount of solvent. Okay, how much can we put in there before we start just dumping extra in? All right, so again, if we want to, I think it's useful to have an image of this. There used to be a PhET simulation, and they took it away, and I don't know where it is, and it made me really sad. But now you guys get to see the power of my drawing skills, so let's draw ourselves a little cup. Okay, so again, this is now, I'm drawing a saturated solution. All right, here's my solid NaCl. So, and then, this is in water. Here's my water. And there's Na pluses and Cl minuses floating around. Okay, if I were to zoom in at this interface, let me change colors. Okay, so now I've got here's my solid. Okay, and here's my solution. I would see Na pluses leaving, and I'd see Na pluses going back in. I'd see Cl minuses leaving and going back in. And those are going to be at the same rate. So again, this dynamic, it is not static. Try and challenge your brain to imagine the chaotic behavior of all of these molecules that are in constant motion, but it's happening at the same rate. And so that concentration is staying constant because as some goes out, some's coming back in. And so when we look at the concentration, it's never changing because we're at equilibrium and the same amount is going in and coming out. All right? So we want to think about solubility, or I'm going to present it as a spectrum. We've got things that are immiscible. All right? So this is the no mixing. Okay, we looked at an example, heptane and water. Now this is hexane and water. These do not mix. Hexane just sits on top of water. All right, it will not go in there. So I would describe that as immiscible. No amount of hexane wants to go into water. Actually, that's not true. No water wants hexane to come in. Hexane would probably be like, great, I would love to interact with you, but water's like, no, thank you. Okay, so it's immiscible. On the other end of solubility, we have miscible. That means I could mix any amount, and it would always mix. Okay, so like ethanol and water, they're miscible. It doesn't matter that I could just keep pouring ethanol in, and it would always mix. I would always have a homogeneous solution. And then there's this in-between range where I have to define it, the solubility of some, it could be 0.01 mgs per mil, right? A very small solubility. I'd call that slightly, or maybe even not soluble, I don't know, slightly soluble. Or maybe I can put a whole, 100 mgs into a mil, right? There's a range here, right? So this would be, maybe I'd call that very soluble, right? But there's a range. Okay, so we're thinking about how much of this stuff can I shove into some of my solution or my solvent. Okay, keeping time here. All right. I want to take a break to just think real quick about what does it look like when molecules versus ionic compounds dissolve. All right, so remember that molecules are best described as ants. Okay, we're not going to disembody them. Okay, so when I put sugar, for example, into water and dissolve it, I still have units of sugar. Okay, I am not splitting apart. I'm not breaking up my sugar molecule. The sugar molecule stays intact, okay? That's in contrast to ionic compounds. If I'm going to dissolve an ionic compound, I have to split it up into its component cation and component anion. This is the part where you remember polyatomic ions, okay? Because we're going to expect you to know those, all right? So these are some of the ones that are especially big to remember, all right? So that if I said, hey, I have ammonium nitrate, what's that going to dissolve into? You could remember what ammonium is and what nitrate is, and you'd say, oh, when ammonium nitrate dissolves, that means I'm going to have NH4 plus ions getting solvated by water, and I'm going to have NO3 minus anions solvated by water. Okay, they have to split apart when they go into solution. All right, so let's look at these two questions. Okay, so is CCl4, we'll call this 1, or calcium chloride more soluble in heptane? All right, so 1 or 2, what's the answer here? Imagine you're sitting in the exam room, you have to answer, there's no point in not answering it. Force yourself, good. Seeing lots of 1s, that is correct. Remember, heptane, our non-polar solvent, does not form strong enough interactions with an ionic compound to make that ionic compound split up into Ca2 plus and Cl minus. Okay, CCl4, remember that was our caveat that this is a non-polar. When it dissolves, let's remind ourselves, when it dissolves, it stays as units of CCl4. I am not when it dissolves, it doesn't become like 4Cl minus and C4 plus, right? That's not how that works. That stays as CCl4, our covalent molecule that's neutral. Okay, that's what we're looking at. Then here I say, all right, this is probably a bad example because they're both really, really soluble. But what I'm getting at here with my comparison between acetic acid and sodium acetate is that I might guess that sodium acetate is more soluble in water because for that to dissolve, I'm going to have to make these two ions, right? That is a salt. So if I'm going to make that dissolve, it's got to go into its two components, right? The two ions. And water is really good at solvating ions, okay? So I would guess this one. Although again, I think that's a bad question because those are both really, really soluble. All right? So we get ion dipole interactions, which are strong. And that's what would drive that. Cool. Okay, so question. If I were to ask you now, is the solubility of a solute a set immutable number? So for example, can I just tell you that the solubility of NaCl is 35 grams? Does that make sense? No, that doesn't make sense. It's context specific, right? So one, we know very well now, hopefully, that the solubility of NaCl very much depends on the solvent, right? What are you trying to put it into? All right, so solubility is solvent dependent. That should hopefully feel like a really comfortable idea right now. Okay, the other big factor that we will discuss, if I increase the temperature of water, will my solubility of NaCl change? Yes. I have intuition because when I put my salt into the pasta water, when it's cold, I can see it sitting at the bottom there, but by the time it's boiling, all of it has dissolved, right? So we will usually see an increase. Okay, so solubility is temperature dependent. And temperature, for the most part, increases solubility, although again, there are some notable exceptions. All right, so finally, if I'm not just going to tell you that the solubility of NaCl is 35 grams. That doesn't mean anything. What I really need to tell you is that the solubility of NaCl in water, that's 25 degrees Celsius, and I have 100 mils of it, that's 35 grams, okay? So it's like really context specific. I got to tell you exactly what am I dealing with here, okay? So let's first look at this solvent. And again, this is like the like dissolves like that we've already talked about, so I'm hoping this feels really comfortable. Our solubilities, we're going to look at alcohols in water. So we're starting with methanol. So alcohols, remember, are OH. That is the alcohol functional group. And then we're attaching it to some carbons, and we're extending the length of that chain. So methanol, ethanol, propanol, butanol, pentanol. All right, so we're just making that chain longer. All right, and if we look at the solubility of these alcohols in water, we see that the first three are all miscible. I can mix any amount of those three into water, all right? And that kind of makes sense with what we were talking about. They look pretty similar. Methanol is pretty darn similar to water. We start getting solubility, like a real number, by the time we get to butanol and then pentanol. And I could predict, if I were going to show you, let's say, like I went even farther, and I showed you octanol with 8. Would you guess that octanol is soluble in water? Like way down here. Right? I'm seeing a trend. It's really big here, and now it's going down. So solubility is decreasing. By the time I get down to 8 carbons, that might not be soluble at all. Okay? So this is a really nice example of like dissolves like. Okay? These two play nice. They mix, they have strong delta H's. But when that pentanol, when I've got that 5 carbon chain and now water has to solvate all of that with no hydrogen bonds, it just says like, maybe a little bit. I'll take 0.03 moles of that for every 100 grams. Okay? This trend flips, all right? This trend flips when we put these things in hexane instead, okay? So now, these are all miscible, right? So our long carbon chains, hexane has no problem with that. It's like, let's party. Methanol is too different. Methanol really likes to hydrogen bond with itself. Hexane doesn't offer that, so it doesn't mix very much. I can only put 0.12 moles of methanol into hexane. All right, the other are all miscible. All right, so we now know. Are we feeling good? Give me a thumbs up that you feel good, thinking good. Like at the very least, you agree with me that the solvent dictates the solubility. Yes? Okay, we're all good taking that home. All right, now, let's consider temperature. This is gonna be our last little thing for today. All right, so here is a graph that you very likely could see on the exam, and we're gonna ask you to interpret it. All right, any question that you get on an exam that starts with a graph, I'm gonna tell you, please start by reading the axes. All right, so on my x-axis, I am increasing temperature. I'm turning up the heat on these solutions. All right, on my y-axis, I have solubility. Specifically, the solubility, so grams of salt in 100 grams of water. All right, so a specific amount of water. All right, as we can make a general statement, okay? I will say that generally, we'll say generally solubility increases with temperature. We have one oddball down here that doesn't follow that trend, and we can, once we get to chapter 19 and we get into the real details of entropy and enthalpy, we could discuss that, but for now, just know that it goes the opposite direction. All right, so generally, temperature is going to increase the amount of solute we can put in our solvent. So for a graph like this, these are the types of questions that you might see on the exam. Okay, so let's take our last 5 minutes of class to take the next 3 to answer these questions, and then I'll go over them, and that'll be it before you guys head off into your early long weekend. Okay, so chat with the people around you if you want to. See if you can interpret these graphs. 50 degrees Celsius. So here, I'm going to walk you through my analysis of a graph like this, right? First off, I'm giving you a temperature. So I'm going to go to that temperature plane, right? So I'm at 50. And then the key here is to say, well, where is my KCl? Where's my potassium chloride versus sodium chloride, all right? I travel up. I hit this. That line is telling me the solubility of NaCl at that temperature, all right? So at 50 degrees Celsius, I can dissolve about 36 grams of NaCl per 100 grams of water, okay? A little bit higher up there is KCl. Let's call that like 42, okay? So my solubility of KCl is a little bit higher than my solubility of NaCl. Does that feel comfy? Okay, higher up, more soluble. So the solubility of KCl is greater. Okay, so that's like 42 grams per 100 grams of water. And this one was only like 36. All right. And then what minimum grams of lead nitrate must be added to 200 grams of water at 20 degrees Celsius to form a saturated solution? All right, so that line is telling me where I hit saturation. I'm going to go to 20 degrees. I go walk up. I hit that yellow line. I say, oh, it's 55. Is 55 grams the right answer? No, because it asked for 200 grams. And then you'd be like, why didn't I read the axis? All right, so for every 100 grams, I can put in 55. But if I double that, I can double the amount of lead nitrate. So 55 grams per 100 grams. So that'll translate into 110 grams of that lead 2 nitrate, okay, that I can put in. Does that make sense? Okay, last question. I've got 2 minutes for it. All right, 3 separate potassium chlorate solutions are made. I put them all into 100 grams of water. One I put 10 in, the next I put 20, and the next I put 30. I want to know if they are saturated or unsaturated, and then I want to compare their concentration. Okay, so let's look at, where's our KClO3? It's right here. Okay, and I'm working at 40 degrees. Okay, let's change color. All right, so we're at 40. Okay, I put in 10 grams. Here's 10, okay? So my 10 grams, I'm underneath that line, okay? All of it dissolves, and I will call this an unsaturated solution. Yes? Okay, unsaturated. My concentration will be 10 grams per that 100 grams of water. All right, and then I say, well, actually, in my next one, I put in 20, okay? I went beyond my saturation point. I went beyond the solubility. This is saturated. Okay, I couldn't put all of those 20 grams in. I can only put in, let's call this 14. I could only put in 14 grams. So I'm going to have probably like 6 grams left over. And then my 30 grams. And this is the place that I want you to be aware, 30 grams. It's saturated, obviously. Does it have the same concentration as the 20-gram cup? If I were to scoop off the top